Good evening and welcome everybody. This is Obi-Wan Pez for N-Simplex Pachinko. We are starting a bit late, but got some mathy type stuff to be doing, so there we go. We're going to be working on our cracking the GRE math test tonight. So we are starting with a few problems that we're looking at. Good. Okay. Okay. So last time we had been talking about, this was 2 weeks ago, so it's been a bit. We were talking about finding derivatives for different functions. And most of the time when we're talking about finding derivatives, then for some function f of x, when we want to take the derivative of that function, we are looking at d dx of that function f, which is the same as taking the limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x. Or, in order to shortcut that, let's say the limit as h goes to 0 of f of x plus h minus f of x all over h. Also known as f prime of x, the derivative d dx of f of x, all that good stuff. So different notations, different ways of saying basically the same thing. Here we were saying that this is looking at the limit of the slope of the secant line through 2 points becoming closer together. So we had been saying that we could take some sort of curve like this, and we could take 1 point here, 1 point here, draw a straight line between them. Okay, and then as we're moving, if we have this distance h between our 2 points, then we're closing that gap between them so that h is going to start approaching 0. Okay. So basically that's where we stand for trying to find values of a particular function. Again, here we'd call this, you know, some particular function, x equals a, and then we'd be looking at the terrible idea, but no, that's okay. That's pretty good. So this particular function here, or this particular line here, is going to have our value f prime at a, that particular point in the function itself. Okay. So that's our basics. Then, in order to extend this to what we actually want to look at tonight, we would want to say, all right, if you were looking for a line that is parallel to another line, that's going to have the same slope. If you are looking for a normal line, it's going to have a perpendicular line, which really means that we have the opposite reciprocal slope. No, that's it here. Okay, so example 2.8 then. Is asking for find the equation of the normal line or find the equation of the line normal to the following curve. Y equals parentheses x to the fourth minus 1 raised to the third power times log of x plus 1. Which goes through the origin. Okay. So if we're solving, we're going to get something that is y minus y1 is equal to the slope that we're going to look at, which is, we'll call it m, times x minus x1. We use point slope form, mostly because this is just the same exact function that we've been working with, where our slope is equal to the difference in y values divided by difference in x values, and then we turn one of the pairs into a variable. So x comma y is just a variable pair. Multiply the x minus x1 to the opposite side, multiply both sides by that. It disappears on the left, moves over to the right. Okay, so it's going to be this, where m is equal to negative 1 over, this is y prime at 0. Right, so the slope has to be the opposite reciprocal of the slope of our curve that we have here. Alright, slope of that particular curve is y prime at any particular point. At x0, y0, or sorry, at 0, 0 for x and y, then we end up getting our function here. Y prime is... No, y prime, there we go. Right, our y value is 0, y prime is not necessarily 0. Y prime could be anything. It just has to go through the origin, and again, with the functions that we have here, log of, remember that this is natural log of x plus 1. Or log with base e. Right, and we can allow x1, y1 to be the origin 0, 0, because again, we know it has to go through the origin. So now y is equal to, this is just negative 1 over y prime at 0 times x. Okay. So y prime of x as a function of x is going to be the derivative of this thing, which, because it's a product between two things, we're going to say what happens if we take the product of the first set first, right? Not product. What if we take the derivative of the first stuff first? So take the derivative of x to the fourth minus 1 parentheses raised to the third power. That's going to cause our 3 to come down front. X to the fourth minus 1 raised to the next step down is second power. Multiply by. This has the chain rule, so we have to then say what is the derivative of the inside stuff? Well, the inside stuff is x to the fourth minus 1. Take the derivative of that, and we end up with, this is 4x cubed. And then we can't go any further once we take the derivative of just the inside here is the derivative of x. So that's going to be 1. Specifically, the derivative of x with respect to x. Alright, then multiply by our log of x plus 1. The second part of our product is then left untouched for the first part of the result of the product rule. Then we say we're now going to add the leave the first part of the product untouched, so x to the fourth minus 1, all raised to the third, multiply by, we take the derivative of natural log of x plus 1, and that's going to be 1 over x plus 1, multiply by the derivative of the inside of x plus 1 is just dx, which again, that becomes dx dx, it's just 1. So now we got this big thing. Woo. The good news is, right, y prime at 0 cleans this up a bit. So 3 times negative 1 squared times 0 times natural log of 0 plus 1 is just 1 plus 0 minus 1 to the third times 1 over 0 plus 1 is just 1. So all of this stuff is now gone. Cleans up very nicely because we had to take the derivative of the inside of x to the fourth minus 1. Just becomes a single term. And then on the other term there, y prime at 0 becomes negative 1 times 1 is just negative 1. Right, so then we go back over here. Say that y is going to be equal to negative 1 over negative 1 times x is just y equals x. I know students who would throw a little bit of a little tiny bit of a fit every single time that something came out to be like, you know, a easy solution. They were like, all that work and this is what we get. It's like, well, but you didn't know that ahead of time, right? There was no way to know ahead of time that this was particularly going to be the answer. And if we just change something a little bit, we say we want the slope of the curve, or slope of the, if we'd wanted the slope of the normal curve to fill in this blank at 2, right? Now you have a general function that you could just plug this all into over here. And we say, okay, plug in 2 for all of this stuff. What do you get? Now it's as simple as just re-plugging in all of the values, figuring out that this is going to get you a different, you know, some different number. 32 natural log 3. Man, don't I feel better already. 16 minus 1 is 15, squared is 225, times 3 is 675. So 675 times 32 times the log of 3. You know, natural log of 3. Man, such a nicer number. Flashbang out. And again, you could figure all this stuff out by saying, like, what is, if we just want, let's go, f of x is equal to, this was x to the fourth minus 1 to the third times natural log of x plus 1. Right, yeah, at 2, we're already way off the chart here. We're just gonna, yeah. But if we had done, like, you know, at 0.5 or something like that, right? We could have come up with this value as well. Some negative 0.33409. Like, it doesn't help me to think, oh, let's go find this really ugly number that's got natural logs built into it. Like, doesn't matter. We can find any value we want in particular. Again, at the origin here, what's our slope? That's going to be f prime of x. Right? There's our value. 0, negative 1. Okay, if you'd wanted some other value, right? What is the slope at that's the maximum, right? That's going to get us a value of negative 0.58. Again, it's something with a natural log built into it. Do I really need that in my life? Or negative 1, 0. Oh, is that actually part of this function? No. Okay. Negative 1 is undefined for this function because, this is kind of important, at the end of this function, we have here the natural log, which is going to get us a negative 1 plus 1 is natural log of 0. And also negative 1 to the fourth is 1, minus 1 gets us 0. This polynomial is going to beat out this natural log here in terms of reaching this 0 value versus the natural log going to negative infinity. Right? A polynomial to the fourth is going to be much more powerful as a term rather than our natural log as a term. And like, we wouldn't necessarily know that. You'd really have to go into finding the limit of their product, which is then going to get us, like I just said, this is now going to 0 rather than going to negative infinity or positive infinity or some other value for that matter. Okay, so then right, this is going to be the equation of the line that is normal to the curve, again perpendicular to this particular curve at the origin, 0, 0. And we can actually see that as well. If we shut this off for a second, and we plug in y equals x, right? If we keep our, let's boost that a bit. If we keep our window such that the distance in the x direction and the distance in the y direction are going to be the same on a visual scale, we can kind of see that here we get something that's approaching a slope of negative 1, right? So we've got something that goes like from negative 0.1 here to 0.1 here with approximately the same value, right? 0.095282. Right, 0.105329. Not the same number. However, when we start getting closer and closer and closer to 0, we notice that it's pretty close, right? It's almost along this diagonal line here. All right, if we go to this one, 0.002, we get negative 0.001998. Okay, negative 0.002. 2002. 2002. Again, really close to being a ratio of like 0.2 in this direction and a negative 0.2 in this direction as we're going around like that. We're getting close. And if we zoom in, the further we get, the more equal those numbers are going to be on the opposite sides, as it turns out, of this slope negative 0.2. So we're going to get closer and closer and closer to having this That's not... Sorry. Closer and closer and closer to having the same value. There we go. So here, again, 1 times 10 to the negative fifth, right? That is a repeated 0.00001, 00001, etc. We're getting close to that. And on the other side here, right, almost the same thing. Realistically, this is just rounding because this has more numbers. This is going to be all, after that point, like 9s, essentially. And then a 0, and 9s and a 0, and 9s and a 0. And that negative is like taking up space typographically. So therefore it's rounding, because after that, where that 1 is should be a 0 with a bunch of 9s after it. And then a 0 followed by a bunch of 9s, and a 0 followed by a bunch of 9s. So again, we're getting closer and closer to this slope of -1, but can't always express it exactly the way we want. And again, here we have an actual slope of +1, so these things are closer to perpendicular as we're getting zoomed in further and further. Okay. All right, so what about if we wanted the line that is parallel to this, right? I mean, we're going to end up with right, the tangent line is going to be y equals -x, and it's not going to be particularly nice, but that's the idea. It's going to be the same work. Right, so actually this is going to... Yeah, right. This is just going to be y equals, again it's through the origin, so it's y minus 0 is equal to -1 times x minus 0 through the origin. So y equals -x is going to be that. And again, if you wanted this to be literally anything else, we could say, okay, let's try again and make it... Hey, Silver. Good evening and welcome back. Yes, this work is highly derivative. Always the math teacher's favorite joke, right? One comma whatever y at 1 ends up being, because I haven't figured it out, right? Gonna integrate some comment. Yep, definitely. Oh, 0. Right. Here we end up with plugging 1 into the function. It's obvious if you just look at it, right? Because it goes through 0 right there. Tangent, oh man. It's got a 0 slope, so that's also kind of boring. You know what? Let's do y equals 1/2, just because I feel like torturing myself. So what is the tangent line at 1/2 by y at 1/2 for this particular function? Again, we have the derivative here. If we say y prime at 1/2 is going to be, and then we try to figure what this is, that's going to be a little bit gross, but it's okay. 3 times. This is 1/2 to the 4th is going to be 1/16 minus 1 all squared times 4 times 1/2 cubed is 1/8 times natural log of 1/2 plus 1 is 3/2. Okay, plus same thing here. It's going to be 1/16 minus 1 cubed times 1 over 3/2. So 2/3. What have you been up to these days? New semester started and all that, or? Okay, this is going to be a negative 5/16. 15. Negative 15/16. Wow. Squared. Times. This is 1/4 of an eighth. Or, no. Wow. This is 4/8. So, 1/2. Times natural log of 3/2. Plus negative 15/16 parentheses cubed times, again, 2/3 is going to be how that untangles itself there. Masters in Engineering Management, nice. Are they telling you how to beat the will out of your workers? I mean... perhaps a low blow. The stick. Week 2, the carrot. Alright, y prime at 1/2 is equal to... so 15 squared is going to be 225 over 256. That's going to be 3/2 stuck out front. 225, 256. And natural log 3/2 minus, so this is going to be a negative number cubed. Carrot is PhD level. 225 by 15. Come on, you can do this without a calculator. Right, 10 and half again. 2250 plus 1125. Okay. The issue I have is mostly bookkeeping in my head. 3375. All right. Times 2. Well, that's fine. 75 over 16 cubed is 2 to the 12th. Man. 20, 40, 8, 40, 96. By 2/3. Yeah. No, we're good. Right, we're good there. This is going to be equal to then. Let's see, 256 doesn't have any 3s, 225 doesn't have any 2s, so we are just multiplying across. This is going to be 512 on the bottom and 675 on top, times the natural log of 3/2. 4096 can be divided by 2, and 3375 can be divided by 3. So that's something. 1125 over 2048. Cool. Is y prime at 1/2. Alright, that is gross. But nonetheless, that number can then be shunted back into y minus. We want y at 1/2 is going to be that thing. It's like almost the same as the first half of this. Negative 15/16 squared, nope, third, times natural log of 3/2. So the cube of 15/16 again is now a negative 3375 over 4096. In the negative, which makes that positive. If we bring it over to the other side, it's negative again. Is equal to this nasty thing.
Rise up from the ashes, wings on my back, stay lit like a matchstick. We ain't coming back, I swear. Just let go and see what happens. Gotta let go to see the magic happen. They got us a quick change, so we like them in phase. I just bought a new watch, time to make my wrist ring.
I'm only slightly salty about management because our president at the community college is still making horrible, awful decisions, and like, I mean, it's basically like taking the decisions that are being made at the country level and shoving it down into the community college level. And it's just like, we're getting enough of this at that level. We don't need you doing it too. And this is x minus 1/2. I don't work there anymore, but we met with one of my friends / former coworkers who's been like keeping tabs on things, and she let me know all sorts of stuff that was happening. I was like, great. There's your line. So for anybody, any students who might be like, why aren't you using just some random number like 1/2 in for your x value? There you go. Yes, in theory, you could just throw that into a calculator and be like, what's the value here going to be? And then we have nicer numbers, technically, but now it's like an infinite decimal instead of being ratios and nice. values, fractions inside of a natural log or something. The other way to then guarantee that you get a nicer looking value at the end is to try and get 1 on the inside of your natural log, which then causes a 0 value for that number. So generally speaking, that's going to be how you do it. Okay. If anybody does have any other questions that are outside of, the curriculum that I'm doing here, feel free and ask, and I will dedicate some time to doing that. So let me know if you have any particular questions, any particular concepts you want to go over, and anybody who's on, who's watching on VODs, come to a live session, and I'll answer, within reason, any kind of math problem that'll take me, a few minutes. If it ends up taking more than like 20 minutes, that might be a question to ask on one of the Discord servers. Okay, so linear approximations is one of those slightly weird topics which, like, most students of calculus will look at this and just be like, why exactly are we doing this? And I never really could come up with a decent answer, I guess, because it was like, well, if you want to figure out what the square root of 2 is or something like that, or like any square root to a reasonable amount, a reasonable accuracy, you can come up with something is a square root, works nicely, that is close to the value that you actually want, and then do this sort of extrapolation from the number that is nice to the number you actually want, which is not particularly nice. And this sort of linear approximation is used in computer programming. It's used in like a whole bunch of stuff. These days, if you're trying to find like actually what's the square root of 2, it's not that hard to do. The computer can do it in millionths of a second or whatever. But I mean, the real answer to why do we do linear approximations at all is it's just a way to understand the concept better. So really what we're doing here is we're trying to show and teach and get you to learn why these things all work the way they do. And once you have a better sense of how it works, then like the calculus becomes almost trivial. The entire subject almost becomes trivial. It becomes so much easier to understand it at an intuitive level that the stuff that is further on in Calculus 1 and then further in Calculus 2 and 3, again, just becomes so much simpler. With our linear approximations, basically what we're doing is we're saying that we want to come up with a particular function where we don't know what a particular value is going to be, but we do have a known nice value. So again, if we do something like a square root function, right, y equals square root of x, and I want to know what the square root of 7.5 is going to be, right, the square root of 7.5 is not nice. And there aren't particularly any values like immediately surrounding this which are nice either. We could come up with some. We could find one somewhere. It's not that bad. But the point here is that what we would like to do is pick a particular value. Let's say 3. This is not going to be a good value. Not 3, I'm sorry. 9, which, when we take its square root, comes back with a known simple value, which again, we know is going to correspond with 3. Square root of 9 is 3. Easy enough. Right, so we get the 0.93 on our function y equals square root of x. Right, and then we want to be like, okay, so where's 7.5 going to be? It's going to be reasonably close to 3. There's our first guess. Okay, how close were we talking? We get something around 4, which again is going to get us 2. That's another nice one that we just know what the value is. That's not actually too bad. Right, we know that this is 1. We know that this is going to be 1 here. Yeah, okay. That's actually a pretty good drawing. Okay, so again, we know that we're going to get a value that for square root of 7.5 is going to be closer to 3 than it is to 2, roughly speaking. And we know that this is going to be a non-linear value. So the closer value, since there's no like really strong change in slope throughout all of this, we can look at this and say, okay, which direction do we want? Do we want a tangent from 4 to get us this value? Or do we want a tangent from 9 to get us this value? And if I'm actually drawing this correctly, this would say that technically the tangent drawn from 4 should actually be slightly more accurate than the tangent drawn from 9. I don't actually know. So this is going to be a fun little experiment. We can check it out. We'll do it from either side. We'll also zoom this in a bit. So if we look at this and kind of like blow it up, what we're going to get is that we have this curve. Right, and we want to know if we draw in tangent from this direction, then what we're going to get is an error, right? This is also going to be the change in y that we're going to get at this particular value. Whereas the change in x is going to be this particular value here. No. It's going to be from here to here is our change in y. Coming from the other way, right? Terrible. That one, and here. No, don't do that. I don't want a curve. Oh, you punk. There we go. Okay. Close enough. So our change in x is going to be here, and our change in y is going to be... Nope. Because it's not to that one. Again, this is to the orange line. Change in y is going to be here. Okay. So then we have to look at this and say, you know, which one of these things is going to be more accurate? Well, we'll see how it goes. But essentially what we're doing is we're saying, okay, we've got a we've got the same stuff that we had back over on down here. Right? The stuff that's right there just on the corner. So we want something that is, you know, parallel to no, we want the tangent line. Wow. To f of x, which in this particular case, f of x is going to be equal to the square root of x at a known location, known nice location. Okay, x 0, y 0. So the first one that we can do is going to be 9 by 3. The second one was 4 by 2. We could do any other pair that we want as well, but these aren't going to, like, which one you pick is just going to make this more or less accurate. It doesn't have to be something that you, like, optimize. Just get something that's nice-ish. Something that you can plug into the function and get an answer back immediately. You don't have to think about it. You don't have to, like, worry that you're, you know, oh no, what if this is going to be... No, just get something that's nice. You can stick it in. You know what it's going to get. Later on, when you become more adept at this, you could say, hey, you know what I'd like to pick? I want to pick 6.25 by 2.5. This is a number that's closer to that other one. Right? This is 25 squared is 625. So 2.5 squared is going to be 6.25. Okay, what about, can we get even closer? Sure, what's 26 squared? Right, 26 squared is going to be 400. 6 times 20 is going to be 120 twice is 240. So that's 640, 676. 6.76, 2.6. All right, we can go even further, right? 2.7. So what's 27 squared? That's going to be 400 and 280 is 680 plus 49 is going to be 729. So 7.29. That's probably the closest we're actually going to get, right? 28 squared is going to be 400, 320 is going to be 720 plus 64, 784. 2.8. Right, so either of those is good. I guess... No, this one's the closest, right? This is optimal if you're doing just 2-digit numbers. And in this case, right, one decimal place. Right? But realistically, right, just go with the two that are here so you could figure this out nice and easily. You didn't have to spend all this time deliberating over, like, oh, what's it going to be? 2.7, 2.8, 2.6, right? The 9, 3, and 4, 2 examples are super easy. You're going to get them right off the top of your head. No worries. Don't have to think about it. So what we're going to do here is we're going to say, find that tangent line. So this is y minus y0. It's going to be equal to m. Since it's the tangent line, we're looking at something that has the same slope as the derivative of this function. F prime at x0 times x minus yeah, right. X minus x0. So we plug in our x0, y0 into those three locations, into the derivative function, and then into the location that we're starting at, the fixed location, x0, y0. Then what we do is we say, okay, so y1, which is the unknown value, is going to be equal to f prime at x0 times x1. No, that's right. Right. We were just looking for the y value. We want to know what the square root of x1 is going to be. So x1 minus x0. Again, x1 is our... you could call it like the test input or something like that. In this particular case, 7.5. Right? X1 equals 7.5 is going to be our test input. So then our y1 is going to be approximately, right? Y1 is going to be approximately equal to the square root of 7.5 to some degree of accuracy. Okay, there's another way that we could express this, and that is that we know that y is equal to square root of x. So if we just take the derivative of both sides, we get that dy is going to be equal to, the square root function is a power of 1/2, so the power rule says that the power comes down. Then we multiply by x raised to that power, 1/2, minus 1. So this is going to be a negative 1/2 times the chain rule, which is dx. Whereas dy dx is equal to 1/2 x to the negative 1/2. We could also leave this as dy is equal to 1/2 x to the negative 1/2 dx. And now what we do is we say, what is the difference between the x values, the one we want and the one we know, and then the y value, the difference in y values is going to be dy. So this may be a little bit weird to look at, but it works. Basically what we're saying is here, again, y1 minus y0 is going to be equal to 1/2 x0 to the negative 1/2 times x1 minus x0. It's the same thing as that one over there. But what we're going to do, if we want the quick and dirty method, again, dy is going to be equal to 1/2 times 1 over the square root of 9 times dx. So dy is going to be equal to 1/2 times 1/3 dx. dy is equal to 1/6 dx. We know that if we were using 9 as our x input, right? So 9 minus 7.5 is a x difference of 1.5. So 1.5 over 6. If that were 15 over 60, that would be 1/4. So it's the same here. So dy is equal to 1/4, which is telling us that if we're going from an x value of 9 down to... No, hang on. If we're going from a starting value of 7.5 up to 9, then our dy is going to start from the known value of 3 and then go up 1/4. Okay, so this is the square root of 7.5, should be approximately 3.25. Terrible approximation, but yeah, that's all right. What's the actual value? I don't know yet. We'll figure it out. If we want to go with the other number, so 7.29 with 2.7. Right? We'll go dy is equal to 1/2 times 1 over. This is the square root of the nice number was 7.29. 7.29 dx. Okay, dy is equal to, this is 1 over twice root 7.29 was 2.7. And that's going to be dx. This is going to be 1 over 5.4 times dx. Our dx in this case is going to be a 0.21 over 5.4. Now this is also another reason that we don't really do like more accurate numbers. You're going to have to do this calculation anyway. So like, yeah, if we throw that in your calculator, it's easy. But again, if you're doing this in your head, that's not, or at least not that much. So a lot of this also, if we're talking about the mechanics of it, and you know, how is this any better than whatever else we're doing? Good, okay. Battery's doing all right. Right, how is this any better than like getting the exact value or just using your calculator? Well, again, it's not. This was invented at a time when calculation was difficult. The best calculating tool was this thing right here. 0.21 divided by 5.4 is 0.03888 repeated. Okay, so that is our dy. Again, dy is about 0.0388. We go from there. It's equal to, but whatever, it's fine. Okay, 7.5 is higher than 7.29, which is the known value. So therefore, the square root of 7.5 should be higher than our known value of 2.7. Okay, that's pretty obvious. Did I mess that up? Oh, did I say between 2 and 3? Yeah, okay. So I screwed it up here. Whoops. Alright, I went up. I should have come down. So going from 9, we had to come down to 7.5. Therefore, to get the square root of 7.5, we have to come down from 3. So that's 3 minus a quarter, which is going to be 2.75. That's better. This is also, see, this is also to help your understanding and your like math sense, because I would have noticed that the first time had I been doing this my entire life, right? You're just like, hey, make sure that you're going the same way, because this is a one-to-one monotonically increasing function. If you're going to the left, it has to be going down. If you're going to the right, it has to be going up. So here, coming from 9, x equals 9, to x equals 7.5, right? We're moving to the right. Therefore, our function value is going to be coming down. Okay. All right, think about it in terms of number sense, and it works pretty well. So here, again, same deal. This time we have to go up from 2.7. So 2.7 plus a 0.03 with 8s repeated is going to be the square root of 7.5 approximated by 2.7388 repeated. Right, 8s repeated. All right. Pretty decent. Again, it's not great, it's not perfect, but it's going to get closer and closer and closer as we pick values that are more and more accurate, more and more close to 7.5. If we want to go to 2 decimal places, that one's probably not going to be so nice. If we wanted to go to 3 decimal places of accuracy, you know, we're going to have to start squaring these numbers, and it becomes, there end up being more and more decimal places in the approximation. So how good are your squares? If you know your 3-digit squares, right, you've got your 2-digit numbers. So you've got 1 decimal place that's going to work for you. If you know your 4-digit squares, then you're going to be able to get probably 2 decimal places of accuracy here. If you know your 5-digit squares, you could probably get a third. So, you know, might work. Okay, so then how do we get the actual value for this? So one of the ways to do this is to say that we can get a better and better and better approximation by taking each of these values. Like, start with a real easy one like 3, 9, and then say, I want to get a simpler, or I want to get a more accurate number than 9. Right? 9 is easy to calculate, super simple. but it's also very inaccurate. And once we start whittling it down further and further, we can get better and better approximations for these particular numbers. So this is where we get something called Newton's method. So yes, Isaac Newton came up with this idea to get values which are successively closer on each iteration in order to make sure that we get more and more and more accurate values. And you only have to do this like a couple of times in order to get something that is, you know, if you're doing it by hand, it's within acceptable tolerance. Let's say 3 iterations. I'm going to bet that we probably don't even have to do 3 iterations here to be within 0.5%. 3 iterations to get 0.5%. I'm going to bet that. So Newton's method says, let's pick a particular value on our function. So again, we're going to go with Right, okay, this is for finding zeros of a function, so I might have boxed myself into a corner here. This is not going to be... This is not going to be a zero of this function. Okay. In theory, we could do this. I haven't done it this way before, but it's fine. What we're going to do is we're going to say that our function, the one that we want to get here, is going to be y equals the square root of x minus the square root of 7.5. Right? So this function right here is going to be y equals the square root of x minus the square root of 7.5. This may cause problems. It's fine, it's fine. At this point, we can kind of just use the calculator and cheat in case we need to, but I want to be able to do this by hand. So... Like I said, this is for demonstration purposes at this point. Okay, so Newton's method, not really what we want. This is for finding zeros. So we have artificially created this this particular function such that this point right here is going to be 7.5, comma 0. Okay, what we're going to do is we're going to pick a known value, which is going to be, this is the nice value, 9, comma 3. We know for a fact that this is not going to have the 0 at 7.5, right? It will have a 0 somewhere further over here. It has a 0 here at this point. Then what we're going to do is we're going to trace this up to this point. We will then take the tangent line at this point and get a number which is right here. Should have done colors the other way around. because, wow, this is going to be terrible. We then trace this up again to this next value, which then this next value has a tangent line. Just going to be over here. And then it's going to keep going and going and going like that. Whoops. All right. Barreled right through those ads. Apologies. This is going to have a more and more and more accurate approximation as we go through the steps of Newton's method. So Newton says, what we're going to do is we're going to take our standard, y minus y1 is equal to m times x minus x1. This is most certainly not in this book, by the way. This is just one of those things that, like, it would be really helpful for anybody to know. And our Calc 1 book that we had did not teach Newton's method. I think that that's probably not very great. Okay. Zero. Let's do x0, y0 first. Okay. So what we're going to do is we're going to come up with the tangent line of the curve that we have. So again, this is going to be f prime at x0 times x minus x0 is equal to y minus y0. Y0 is the original function at x0, and on our next step, so in other words, when we do this as x1, y1, we want y1 to be equal to 0 because we want to know where this function hits the x-axis. So our y value is going to be equal to 0 at this particular next point. So we have the approximation that y0 is going to be 3, x0 is going to be 9, and then next, our next point is when y1 is equal to 0. And then we have to find what the x1 value is when y1 is equal to 0. So here, 0 minus f of x sub 0 is equal to f prime at x sub 0 times x sub 1 minus x sub 0. Again, we already know what most of these values are going to be. We need to find what is the value of x sub 1. So, start uncovering stuff. This is going to be a negative f of x sub 0 over f prime at x sub 0 is equal to x1 minus x0. Shift the other thing over, and x sub 1 becomes x sub 0 minus f at x sub 0 over f prime at x sub 0. More generally, what's going to happen on the next step? We're going to find x sub 1. That's going to go in to the function, the derivative, and the x sub 0 spot. And then we get x sub 2 as the next x value. So generally speaking, this is going to be x sub I plus 1 is equal to, I need to move that over, Wasn't thinking about that. Okay. X sub I plus 1 is equal to x sub I minus f at x sub I over f prime at x sub I. Okay, so using Newton's method, we can now figure out what the square root of 7.5 is going to be. Again, we have to cheat a little bit because we don't know what the square root of 7.5 is. So therefore, when we plug it into f, it's going to be involved here. The calculator comes up with a decimal approximation. It feeds it to us, and then it's going to be part of our next x value. So again, sort of cheating, but there are other ways to do this also. Okay, so this means that x sub 1 is going to be equal to x sub 0 was 9 minus f at x sub 0 is square root of 9 divided by f prime was again 1/2 times 1 over square root of 9. So here, this ends up being a, again, root 9 is 3. This is 1/2 times 1/3 is 1/6. The 6 then, we can multiply both top and bottom, and it gets knocked up to the top. And that, oh, whoops, yep, minus root 7.5. Sorry, that's the function value, so we have to watch that. In theory, again, this doesn't really work because we don't know what square root of 7.5 is. But in practice, we can just let the calculator figure it out for now. So x1 is going to be 9 minus, this is 6 times that difference. 3 minus root 7.5. So x1 is going to be, give or take, okay, we take y1 at 9, and we end up getting a 0.26. 9 minus 6 times, that's higher, so 0.26138722125 more stuff. Right, so we multiply that by 6. We'd say 9 minus that answer is going to get us x1 is approximately 7.4316776725. Not bad. Right? 7.43 is much better than 9. Hang on. Sorry, I don't want the square root of 7.5. I want... Yeah, no, sorry. I want the square root of 7.5 to show up here. So this is actually a terrible number, but it's fine. Hang on. Oi. No, this is going to come up with 7.5. Okay, so I screwed this up. I played myself here. Our x values are trending toward 7.5. Damn. This is not a square root algorithm. I went backwards. Okay. Man. Right, these are to find x values, not y values. Boy. Screwed that up. Alright. On the other hand, hang on. We can fix this. Because again, we want x values, right? So that means that if we choose y equals x squared minus 7.5, I think that'll actually get us what we want. Right, 7.5 here. It's going to come up like that. Right, where is y equal to 0? It's when x squared is equal to 7.5. Therefore, right, and x is greater than or equal to 0. Right. 0 at 0 equals x squared minus 7.5. So 7.5 equals x squared. So therefore x is equal to root 7.5. Okay, this is going to work. So apologies. We're trying to find x values with Newton's method. So Newton is going to get us to this point. We say here's our function y equals x squared minus 7.5. Now we want to find the 0 for that, which is going to be at x equals root 7.5. The positive one. Right, we're going to ignore the negative one for now. Okay. So what we're going to do is we say that our first guess was up here at 9. Which is where x is equal to 3. Which is going to get us this value here. When we do that, then that's going to get us this value here. When we plug it back into the original equation, we get its tangent. Okay, we get its tangent line, which is going to be here, which should be again short of the value we want, but it's going to be in there. Right, which is going to be closer, which then we get another, and another, and another, as far as we want this to go. Okay. So, find any square root you want. In order to do that, find when the x value, which goes inside the square root, is going to get us... Yep, is going to end up being squared to get us that value here. So the square root of this thing is what you're looking for. Hey Famished, how's it going? Straight from El Salvador. Ooh, what you got? Are you in El Salvador right now? I could not possibly guess what this could be. Hey, there we go. Dost thou in hoist? Righto. So, good times. As always, we're going to start out with our 20 pounders. These are, roughly speaking, just under 10 kilos, and we just do some lifting every time that somebody asks for it. Just keep in shape, all that good stuff. Too hot here? Yeah, I also appreciate rain when there is much less. Although, I guess, down there, is there a rainy season? Alright. Lift. Happens in the afternoon a lot. Yeah, at least gives you time to do stuff, yeah. What you doing in El Salvador? My cousins lived there for a few years. Alrighty, good times. Ooh. There we go. Yeah. Alright.
And listening. You can tune in anytime, anywhere. Got a show of your own? Upload your video to Spotify. Turn views into fans and monetize your passion. I lost my best friend at 23. She left her body and hovered above me. I saw no shadow. I looked around.
Okay, so Newton's method in this particular case is going to get us that our x1 is going to be equal to, this was x0 minus f at x0 over f prime at x0. So we're going to get, again, 3 minus right. F at x0 is going to be 3 squared is 9 minus 7.5 over. Now we take the derivative of that function, which is going to get us 2x. That's it. Oh, tooth extraction. Yeah. Medical tourism. I'm sorry. It's ridiculous. What do they want to do to it here? Or, well, in the US. It is sadly common, yeah. I've got pretty good dental coverage, so I never have to actually worry about it, but yeah. Alright, so f prime in this case is just going to be, again, 2x. That's it. So this is twice. Our x value was 9. Okay, so we get 3 minus 9 minus 7.5 is 1.5 over 2 times 9 is 18. Pretty nice. So this is going to be 3 minus 1.5 over 18. We can divide both by 3, so we get a 0.5 over 6. Or 3 minus 1/12. Yep. Got to do what you got to do, and especially I know that mine was just my nerves coming back online after anesthesia, but yeah, like tooth pain is absolutely insanity. You don't mess with that. That's okay. So 3 minus a 12th. Is going to be 2.9. 2.916 with repeated 6s after that. Okay, so then we do the same thing over again. And we say that we're going to do this a little bit faster this time. x2 is going to be x1 minus f of x1 over f prime at x1, which again are just these particular numbers that we were looking at. x2 is equal to, this is 2.916 repeated, minus root 2. No, that's not root. Jeez. 2.916 repeated squared minus 7.5 over twice 2.916 repeated. So what we're going to do is we're going to plug in on our y equals on the calculator, hashtag not sponsored, our y1 is going to be the function. So in this case, it is x squared minus 7.5. y2 is going to be the derivative function, which in this case is just 2x. It's nice and easy, but we want to set up an algorithm to make this work. What we do is we say, okay, our first number was 9. No, our first number was 3. Again, I did it again. First number was 3. We're going to store that into x. So 3 stored to x. Looks like that. The store button is just above on here, STO arrow. And if you hit 3, store, and then the x variable key right here, something like that. Come on. Come on. There we go. xt theta n, it'll pop up with x because we're working in function mode. So 3 store to x, hit enter, it'll say 3 because now it just stored the 3 into the x. Then what we do is we say, okay, take x, subtract. There's a complicated set of keystrokes here, but it works pretty nicely. If you're doing this in anything else, literally, I don't know how to do it, but it shouldn't be difficult if you're like programming or whatever. But there's a vars key here, which if you hit that, it pops up with a bunch of stuff. All right, if we go over to yvars, we are in function mode. And now it says y1, y2, etc. So we do y1 divided by, oh no, y1 at x. So put the parentheses in there. y1 at x divided by vars, yvars function y2, which is our derivative function, parentheses x. Okay, if we want to check it just to make sure our programming is working, hit it. All right, what did I do? How did I screw this up? What is y1, just y1 at x? Oops. 1.5. Okay. What is... oh. Yep. I did it again. It was this 9 here is not a 9. Boy. This is a 3. So that's a 6. So this is going to be a 1/4. Which actually, right, is the exact same thing that we got in this formulation of it here. Right here. Is this the same? Yeah, this is the same formulation. It's just done a little bit different, so it's all good. So here at the bottom we see that this is twice our original x value was the square root of 9 is 3. Oh, jeez. And our dx was then going to be 1.5, so therefore we end up getting a 4th. It's, like I said, it's the same formulation. I just screwed it up. It's fine. 1.5 over 6 is the same as 1 over 4, which now, again, is 2.75. Okay, now we come back over here. Boo. 2.75 minus 2.75 squared minus 7.5 divided by twice 2.75. Yeah. That's nice to at least be able to get something like, you know, positively done, even if it's going to cost us. I don't know. Making glasses down there, it depends, right? If you just need like reading glasses or whatever, those are cheap. You can get them practically anywhere in the U.S. But if you need a prescription, I don't know. I know our neighbor's daughter had a prescription that ends up being like, you know, $400 every time she breaks her glasses, so and she's rather accident prone. Okay, so one more time here. Right, I did not mean to clear that out. That's fine. You know what? It's fine. What is x? X is still 3. Good. So now we do x minus y1 at x divided by y2 at x. Alright, which again gets us 2.75. So now we've actually got the right answer in here. Or rather, the calculator had it right the whole time. I was the one who screwed it up. No surprise there. Alright, now if we go back and now store this value itself back to x again, it will overwrite the 3, which means that now it's still going to say 2.75. But that just means that it now plugged in 2.75 for 3. So if we hit enter again, this is going to, this is going to take 2.75 and plug it into all these values. And we end up with a value of, boop, 2.73863. More stuff after that. So y2 is going to be 2.73863634. And actually, that's just 6-3 repeated. Right? That's just going to keep going. So if we reiterate, right, x3, x4, x5 are going to be 2.7386127888, and x4 ends up being the same out to as many decimal places as this has. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if you do this on like MATLAB, or so many of you will not do it on MATLAB. You will do it in like Python or whatever, you know, and use NumPy.
This is an ad by BetterHelp. We've all had that epic rideshare experience. Halfway through, your best friend
right, use NumPy or one of the other libraries. I don't know which ones are actually going to work for you these days, which ones are good or whatever. I'm a bit out of the loop. It's fine. NumPy never worked for me properly. I don't know if it was just the version that I was using because I'm on Linux or whatever. Right, so then x5 is also going to be the same to 9 decimal places. It's never going to change. This is just going to get better and better and better of an approximation out to as many decimal places as we need it to go. So yeah, it's fine. So this is going to get us that particular value. All right, what was the actual value then? The square root. I mean, it's that decimal approximation. Yep. So in 3 iterations, like doing the calculations 3 times, right? Gets us the same number as the exact value out to 9 decimal places. Right, and doing it twice got us the same number out to here. So 4 decimal places of accuracy plus the 1 number out front. So let's actually look at how accurate that is in the first place, because I said I want this to be within like 0.5%. I think we've got it here. But yeah, so our actual number again, root 7.5 minus this number, 2.73863 with the 6.3 repeating, over the exact value of root 7.5 times 100%, you know. Okay, parentheses, root 7.5, oops, not there, minus that number over root 7.5 gets us this should be absolute value, but no big deal. 8.60891116, not that any of that matters, times 10 to the negative 6th as a raw input. So as a percentage, this is 0.0 Let's see. 1, 2, 3, 4. 0.89% error. So I said 0.5%? Yeah, we're there. All right, 1, 2, 3, 4. Yep. So Newton's method is extremely powerful out to, you know, however many decimal places you want. How much time do you have, and how much computing power do you have? If we're doing stuff like what I've just done here, where we're just plugging function values in, like, your calculator can do it. It's not a big deal. If it's some weird function that takes, like, you know, a minute to calculate a number, that becomes more difficult. But we're still going to get a quickly, generally speaking, we are going to get a quickly converging value for the correct answer. You do have to watch out just in case. Sometimes it will not be quickly converging because if you get near your zero, if there's like a really steep area followed by like less steep areas out from there, we may have some problems. But as long as you don't have any actual singularities, so if you have any asymptotes or discontinuities, that's a problem. If your derivative function has a lot of zeros, that could potentially cause a problem because it's in the denominator. So if it has a lot of zeros, we could get really close to a zero, and something that is a zero in the denominator causes serious problems. Something that is close to a zero in the denominator can cause this whole thing to blow up real fast. So we do like it in like stabilized regions of your function. And most of the time it works great. So I think this does actually come from like an algorithm that people had suggested for coming up with square root values. So if I want the square root of, you know, so let's not do 7. Let's do like 527. Right? Again, we could come up with a reasonable approximation for this, or we come up with a linear approximation, or we can use Newton's method on something like this. So we would say, like, we want 0 for x squared minus 527. Right? What number, when you square it, will get me 527? So then here we convert this into what is the 0 for this function, x squared minus 527. The closer we get to 527 as our x squared value, the closer to 0 our y value becomes, until we get an exact value. So a reasonable approximation for finding a reasonable approximation for this is going to be used from taking a value which is, again, reasonably close. So what is 24 squared? It's going to be 400. 80 is 160, so that's 560. 576. 23 squared. 469. No, 529. Ooh. Right, so this is 400. The middle terms are going to be 60 times 2 is 120. So 400 and 120 is 520, and then the 3's squared gets you 9. Okay. For anybody who's not familiar with this, I'm using the binomial method in order to figure out these squares. So this is 20 plus 3 parentheses squared. So how do we find it? Right, it's x squared plus 2xy plus y squared. So 20 squared gets you 400. 20 squared gets you 400. 3 squared gets you 9. And then the middle ones are 20 by 3 is 60. Doubled is 120. So 400, 120, and 9. Okay, so that's actually really close. 23 would be a reasonable approximation. Right, so in doing this, we've got now x sub 1 is going to be x sub 0 is again 23 minus if we plug in 23 into this, we get 529 minus 527 is 2. Divided by the derivative of this is going to be 2x again. So this is going to be twice 23, our number that we were plugging in the first place. Right, so this ends up being like if we were to kind of simplify this to say, you know, what operations are you doing in your head real fast, right? This is your whatever x value you're currently at. So this is your close root. Minus your dy, delta y. So this is your difference in square numbers over twice your close root, right? 2 times whatever x value you're currently at. $23 minus the 2's divide out, so that's nice. And you got 1/23. Doesn't always happen, but you know, pretty nice in this case. 23 minus 1/23 is going to be x1 is 22.956. 2174. And now we go through the same process again using Newton's method. We say x2 is going to be 22.956, etc. minus that thing squared minus 527 over twice its value. Okay, so let's go like this. We're going to go 23 store to X, and that, nope, not trace. Boo. Go back up to here. And now we plug this in. No. No, that, no. I'm getting 5,000. That's, no. What did I do? No. Oh, I forgot to... I forgot to change 7.5 to 527. There we go. Very important, people. Make sure that you're actually doing this right. Okay, so x squared minus 527 is going to be our value. We want to store 23 into x. And then use this thing, which now gets us, there we go, 22.95652174. Yes. Again, gets us x2 is 22.95648057. And x sub 3 is the same. So again, now in 2, because we had a good approximation to start with, i.e. 23 got us 529, right? The square root of 527 is now going to be that to 9 decimal places. So 22.95648057. Awesome.
Spotify Premium is what your ears deserve. With millions of songs and high-quality audio, treat yourself to limitless music. Get 3 free months now and cancel anytime. Tap the banner to learn more.
So depending on how much time and processing power you have, again, Newton's method makes this all so much easier. If you have a decent approximation nearby, that works pretty nicely. Okay, so now let's go back. Our example is going to ask find an approximate value for e to the 0.1. Okay, so generally speaking, anytime you have transcendental numbers like this, where you have like e or natural log, or, I mean, even square roots are pretty bad, but e and natural log are notorious. So for this kind of stuff, we just want to pick values that are nice, like a lot nicer. So here, we know that e to the 0 is going to be equal to 1. That's going to be the nicest value that we could probably find for anything that you want. We could probably say, like, okay, the natural log of 2 is going to be our first, like the first value we pick. Or, let's see. We don't have any nice values for this, but right, this is yeah, no. We don't have any nice values for this. We could, in theory, work out something else with a different log, maybe like log base 10, because this is a 0.1, and then figure out some other way to make this work. But I mean, quite frankly, this is not going to change my mind at all. This is the best number we can find. So we know that this is accurate. And again, so what we want is f of x is equal to e to the x. f prime at x is going to be equal to e to the x. Or, a better way to say it, right, is that our df is equal to e to the x times dx. I much prefer to do this in the implicit differentiation type way, because as a teacher of differential equations, you create differentials. That's what you do. It's a way better way to do this. The other thing is that here we can now use this approximation, or use this as part of our approximation. So here we want to say that our df is equal to, we have, again, e to the 0 is the nice value that we're using, times our dx is going to be, what's the difference between that and that, right? Between our 0 here and our 0.1 here. It's 0.1. In what direction? It's higher. How do exponential functions work? They're monotonically increasing. So as we move to the right, it will always move up. Right? It makes it much easier to like think this through. Essentially, df says that we're going to get 0.1. So that means that e to the 0.1 is going to be approximately 0.1 plus e to the 0, which is 1.01. Right? Close enough? Well, let's find out. So here, e to the 0.1 is... Oh, no, not... Check your decimals. Oh my goodness. I teach math. Right? 0.1 plus 1 is 1.1. Alright, whereas from the calculator, e to the 0.1 is going to be equal to 1.105. 170918 with, you know, other stuff after this. In fact, that 8 might be a lower number and then round it up to 8, but whatever, it's fine. This is what we're going to get. So, is that good enough? Well, there's one way to find out, right? We plug this into our absolute value, 1.105170918, etc., minus 1.1, all divided by 1.105170918, etc. Right? So, we do, parentheses, e to the 0.1, nope, 0.1, minus 1.1 over e to the 0.1. Keep hitting the negative button. Is a 0.004 788, good enough, right? Which is a percentage of 0.46788%. Again, within a 0.5% error, so that's, you know, very good. And again, if this is one of those things where you're like trying to, you know, be within a 2% tolerance or a 0.5% tolerance, again, you've succeeded. So we're done. All right.